In this question, we're told that water flows from this storage tank and it travels through a pipeline which is 170 meters long and 150 millimeters in diameter, and it's made of cast iron, as shown in the diagram. And we're told to calculate what the height of water is, Z1, if the volumetric flow rate through the pipe is 0.07 meters cubed per second, and we'd be also given the viscosity of the water. So first thing we need to do in this problem is, because we want to find this pressure head term, is to write down Bernoulli's. So we've got the static pressure plus the dynamic pressure plus potential pressure is equal to 0.1, which is at the surface of the water here. And that's equal to all the conditions at the exit, plus this additional term, the pressure loss term. Now we can simplify Bernoulli's because we know that, we can see that this tank is open to the atmosphere, so the pressure at 0.1 is atmospheric pressure, and also because this pipe is discharging into the atmosphere, then also the pressure at 0.2 is also atmospheric, so they're equal to each other. So P1 and P2 are atmospheric pressure, so you can see that they will cancel. We can also, if you remember when we were looking at the Bernoulli's equation, make some assumptions about the velocity. So because this tank, we can see is very large in area compared to the area in the pipe, then the velocity in the tank is going to be very, very small compared to the velocity in the pipe. So therefore we can say that the velocity at 0.1 is negligible, or in fact it's zero. So this dynamic pressure term will also disappear because it would be set to zero. And because we're going to take 0.2 as our datum to work out Z1, then we'll say that Z2 is zero. So you can see this Bernoulli's equation here will simplify to this expression. So we're trying to find out Z1. We can calculate the velocity because we were told the pipe diameter and the volumetric flow rate, so we can find that velocity. So what the other term that we need to find is pressure loss. Okay, and this is a type 1 problem because we just need to calculate the pressure loss, and we know the volumetric flow rate, so we know the velocity, and also we know the pipe diameter. So first things to calculate the Reynolds number, but to do that we need to know the velocity. So from the volumetric flow rate and the diameter of the pipe, we can calculate the area, which gives us a velocity of 3.96 meters per second. Put that into the Reynolds number along with the fluid properties and pipe diameter. That gives us a Reynolds number of 3.9 times 10 to the 5. Now we weren't told what the surface roughness, the pipe roughness was in the question, but we were told that it's cast iron. And if you remember, in the bottom left hand corner of the Moody diagram, there's a list of typical roughnesses for common materials. So we were told that it's cast iron, so if we look up cast iron on this list and read across, we can see that it has a value of 0.15 millimeters. Okay, we need to make sure we've got it in the right units. So therefore we can then put this in to calculate the relative pipe roughness, which comes out to be 0.001. So now we've got everything we need to calculate the friction factor from the Moody diagram. So we know our Reynolds number, which is 3.9 times 10 to the 5, which is around about here. And we know our relative pipe roughness is 0.001, so we're on this line. So we need to find the point where these two intersect, which is just about there. And if we read it off, it's around about 0.02, the friction factor. So from the graph, we said it was 0.02. And again, just to show you, if you were to use the formula, you get it ever so slightly more accurate. It comes out at 0.0203. We have this friction factor, so we can put that into the Darcy Weisbach equation. We know everything else. We know the length, density, velocity, and so on. And so that gives us a pressure loss of 181 kilopascals. So that's not the last part of the question. Remember, we're trying to find the height of the reservoir to give us that volumetric flow rate. So This is the equation we simplified from Bernoulli's. So we rearranged to make z the subject, put in all the other values that we know that we've worked out, and if you plug that into a calculator, you should get an answer of 19.2 meters, which is the height that you need for that given for the flow rate that was specified.